Welcome back, Lecturer Joe here. Today we're going to look at the numbering system known as binary, because that's the numbering system used within all computing, PLC, all digital electronics. So it's really important to get your head around this. So binary numbers look like this. They are numbers that are composed of only zeros and ones. Only two possible symbols, a 0 and a 1. And the reason for that is that an electronic switch can either be open or closed. So pretty much all of digital electronics involves switches being open and closed, and that can be represented as a 0 or a 1. Switch open is a 0, switch closed is a 1. So there's a whole numbering system that uses only zeros and ones to represent any quantity. The best place to start when trying to understand binary, in other words, what sort of value is this? Is this 158 or 27? Or the best place to start is to go back to how you actually learned the conventional numbering system, decimal, that you're familiar with. If we go back and look at how you learned that in primary school, it'll make the binary a wee bit easier to understand. So let's take a look at that first. So here's our random number, and you recognize that as 743. It's made up of three symbols, a 7, a 4 and a 3. But this represents hundreds, this represents tens, and this represents ones, on account of their position. So back when you were in primary school all those years ago, you were shown something like this that you may not remember. Ones, or units sometimes it was called, but essentially ones, tens, hundreds. So the position of each of these digits tells you something about its value. Not only is this a 7, but it's in the column for hundreds. Not only is this a 4, but it's in the column for tens. So this number is 7 hundreds, which is 700, 4 tens, which is 40, and 3 ones, which is 3, all added together, 743. And if there was another digit in front of this, let's say a 2 there, that would be thousands, and we would have 2 thousands added onto that. 2 thousands, 7 hundreds, 4 tens, 3 ones. 2,743. Now before we look at binary, let's remind ourselves what's going on here. These columns, 1, 10, 100, 1,000, each column is 10 times bigger than the previous column. That's why this is the base 10 numbering system, or decimal numbering system. The other thing worth noting is that we have 10 different symbols we can put in any of these columns, but they're not the symbols 1 to 10, they're the symbols 0 through to 9, because we would never have two numbers in a single column. So the fundamental symbols that we work with are those, not through to 9. These are the only symbols that can appear in these slots. Each slot has to have one of those symbols in it. So what if instead of 2,743 we had the value 2,000s, 700s, no tens, and 3. 2,000s, 700s, no tens, and 3. Well, we couldn't write that as 273 because that's going to look like 273. So into the slot for the tens we have to put the symbol for 0 to show that there aren't any of those. Now this is a really important idea. There was a time back in sort of Roman times, 2000 odd years ago, they had a numbering system. You've probably seen some of the symbols, X, V, 1, C, these sorts of things, where each symbol represents a quantity, just like these. But they had no system like this. They didn't have a symbol for 0. I mean, after all, if you need to specify 0 sheep, why do you need a symbol for that? You need a symbol for 10 sheep or 5 chickens. But if there aren't any sheep, why do we need a symbol for it? So this system just simply uses each symbol to represent a value and then you add them together. But there isn't a kind of background frame where the position of the symbol carries any importance. As soon as this idea was cooked up, we needed a symbol for nothing, a symbol for 0. And there was actually a point in time where this was thought up. We need a symbol to represent no quantity. And it was only with the invention of this symbol, the invention of the idea of 0, that we got this sort of numbering system and mathematics really took off. So although the Romans did a lot of great stuff, building monuments and all the rest of it, conquered the world, they weren't too hot on the mathematics, because mathematics, when on this sort of basis, is extremely difficult. As soon as you adopt this system where the position of the digit is important, mathematics becomes much easier. And when you adopt that, you need a symbol for there's nothing in that slot. We need a symbol for 0. So enough of the history lesson. Let's look at binary. Just before we leave this, let's recap. This is decimal, which is the numbering system you're familiar with, also known as base 10. The 10 refers to the fact that each column is 10 greater than the previous column, and also refers to the fact that there are 10 symbols, and those symbols are 0 through to 9. And you'll notice that the largest symbol you can have there, 9, is 1 smaller than the base, because when you go 1 above that, you put a 0 here and move your 1 across. So bear that in mind when we look at the binary system. So our decimal system is base 10, our binary system is base 2. And remember, in the decimal system, the largest symbol you could represent was 9, 1 less than the base. Here, the largest is a 1. And we still need a symbol for nothing, which is 0. So these are the only 2 symbols that make up numbers written in binary. So here is a number written in binary. Not sure yet what value it is, we'll work that out in a moment. But you can't have the digit 2 or 3 or 4 in here. It can only be 0s and 1s. Let's move that down to here and we'll work out what value it has. Same rules as before. We've got columns. Each column represents a value, but instead of being 1s, 10s, 100s, where the columns go up by a multiplication of 10, here they go up by a multiplication of 2. So these are 1s, 2s, 4s, 8s, 16s, 32s. Once you understand that, you understand binary, because this is made up same as before. We've got a 1, no 2s, a 4, no 8s, no 16s, and a 32. So add them together like we did before with our 1s, 10s, 100s and 1000s. So we're sitting with 32, 36. So this value in base 2 is equal to this in base 10. So the quantity 37 is represented by this symbol. if we're using base 10, as we normally do, and the quantity 37 is represented by these symbols if we're using base 2. These are both the same quantity, just using two different numbering systems. The numbering system we're accustomed to, and the numbering system that computers are accustomed to.